All right, so probability of success is going to be equal to 1 over 1 plus e to the minus negative 0.288 plus 1.229 times 1. Again, for obvious reasons, we're looking at the probability of success given that they did attend the Friday sessions. And I get 0.719 here. So guys, the probability of non-success is going to be 1 minus 0.719. So that's 0.281, right? All right, cool. Now, let's get into the odds. So the odds are going to be 0.719 over 0.281, and I get 2.56. Well, guys, this now brings us to the odds ratio. So our odds ratio is going to be what? What do you think? It's going to be pretty much what? The odds after a unit change divided by the odds of the baseline, the odds of the original. So in other words, the odds ratio is kind of the change in odds from x equals 0 to x equal 1. So guys, at the end of the day, there we go again. That's hilarious. So the odds after 1 unit change over the odds of the base. So I'm going to have to look this up, guys. I don't remember. Was it 0.22 or something like that? So 0.256. No, 2.56. Over 0.748. And I get 3.42. So guys, this will be the odds ratio. And this just estimates the change in the odds of group membership for our target group, which is the success for a 1 unit increase in the predictor. I need to write that down. I need to tell you that. So 3.42 estimates the change in the odds of group membership. And this is for our target group. So we you know, in our dependent variable, we get a target group, and our target group was success, and again, that's typically going to be what you're going to code as 1. It makes the interpretations easier. So let me get back. 3.42 estimates the change in the odds of group membership for a 1 unit increase in our predictor. All right. Well, gang, hopefully this is becoming a little bit clearer. Odds ratios are always a little frustrating to calculate because they take such organization, keeping your zeros and your ones and everything. But it's just something you got to do early on. I tried to point this out in 5500, but that's been a while since you've taken that. It's really important to decide what your baseline is going to be. And not only do you have to just kind of wrap your mind around it, you need to make sure when you start your examining data using R that you go ahead and set your baseline. Well, gang, there's another way. And this other method is much easier. So there's another way of expressing odds ratio. Is also can be found by raising e to the base b. I would think usually this is preferred. I prefer it because it's easier and it's just a straightforward calculation from our beta. So guys, recall our beta is equal to 1.23. So clearly if we have e raised to the 1.23, appreciating that we're going to have a little bit of a rounding issue. I get 3.42, which should look familiar. Now, guys, I want you to be able to do both ways of calculation, and you'll see that on your assignment. All right, gang. There's ways to do this in R, as you would imagine. Let me point that out to you because it's clearly something that's that we'll run into. One kind of really cool way, again, I forget what we call a model. We'll call it model. Okay, if you go model $ coefficients, well, if I could spell, actually I can spell. What it'll do, it'll give you the coefficients of the model as we saw up here without standard error and test statistic and p-value. And if we want to do the EXP of model coefficients, we can get this, and we can see that the 3.42 that we calculated not only by hand and not only by raising e to the b power, we can see that R gets us these values very quickly and very efficiently. Now, in terms of odd ratios, we have to consider that the balance point, for lack of a better way of putting it, is 1. So 1 says that the odds are equally likely. We don't run into many situations where we get odds ratio of 1. We usually get something above or something below. I think I've mentioned this in a previous video, but it's certainly worth repeating. When we get into our odds ratios, we have 1 as the balance point, if you will, ranging down to 0. Again, this just says that the outcome is equally likely, contingent upon a 1 unit increase in our predictor. This down here, if we get a odds ratio between 0 and 1, this tells us that as the predictor increases, increases 1 unit, the odds of the outcome decreases. All right, sorry about that. And of course, as the predictor increases, one unit, the odds of the outcome, in our case, success, increases. Now, what I want to do next is I want to get into confidence intervals. And again, if we can bounce this off something we already know how to do. If I'm testing that mu1 is equal to mu2, and testing the difference mu1 not equal to mu2. Okay, so I'm testing the mean difference is equal to 0 versus the mean difference is not equal to 0. If I get a confidence interval that looks like this, my immediate attention is brought to the fact, does this interval contain 0? Because if it contains 0, then it's more plausible for me to believe that the mean difference, mu1 minus mu2, is equal to 0, lending support for there's no difference in the population means. So our focus on problems like this is on 0. In odds ratios, our focus isn't on 0, our focus is on 1. So when we create confidence intervals for our B's, that's actually our focus. Now, don't get confused on this, because if I go over to R and let's just say that I just a straight out confidence interval. This really doesn't mean much to me. You look at that, if you get sloppy, you'll say, well, that contains 1, and you don't have statistical significance. But guys, what we need is the EXP of the confidence interval, for obvious reasons. In this situation, we see it is above 1. So again, as tutor moves to yes, it moves from no to yes, so a 1 unit increase in our predictor. The odds ratio, well, there's a 0.95 probability that the odds ratio is between 1.58 and 7.63. Okay. And again, focus, does it contain 1? If it contains 1, then our predictor is not going to be statistically significant. So, but guys, again, in interpretation, our confidence interval will be 1.58 to 7.63, and there's a 0.95 probability this interval contains the population odds ratio. Now, what I want to do, just very quickly, I think I'm running out of time here. I would like to look at the 2 predictor model. I don't want to get into a lot other than I want to just look at I just want to glance at things, okay, and just point some things out to you very, very quickly, okay. So what I'd like to do now is I'd like to run a second model, and I'm going to call this Model 2, and pretty much replicate what I just did for the single predictor. So what I'd like to do now is I'd like to bring in this MyMathLab component and see if the number of days that the students spent 1 hour or more on MyMathLab was actually helped predict course success. All right. So, gang, in doing that, we should know that we can calculate the Model 2 by taking the general linear model of success over tutor plus MyMathLab. I think it was all caps. And family is equal to binomial. So guys, we can run a summary of Model 2, and we get stuff. Now, what jumps out to me, again, I'm kind of thinking threefold here. I'm always interested in the number of iterations. Again, it's 4. I'm always interested in a breakdown of the coefficient analysis, and I'm always interested in a breakdown of the model analysis. Now, I want to take a look at the coefficient first. So when I look at the coefficients, I have Tutor and I have MyMathLab. So a 1 unit increase in Tutor, which is categorical, meaning it moves from no to yes, is still statistically significant in predicting course success. MyMathLab, on the other hand, which is a continuous variable, says that 1 unit increase means what? Well, that was just one more day that they spent at least 1 hour on MyMathLab. You can see that this predictor is not statistically significant. Now, moving to the model analysis, I don't remember exactly, but I think I can go back up here and look. When we had a 1 predictor model, our residual deviance was 144.16. And I know this has changed a little bit, but rounded to 2 places, the residual deviance is 144.16 on 110 degrees of freedom because we have 2 predictors. It hadn't changed any. The AIC, let's see if it had to go up, right? AIC, again, is a measurement that the higher it gets, the worse model we're getting. So it increased from 146 to 150. So all things are pointing now toward adding this extra predictor created no change in the effectiveness of the model. So if ultimately the goal is to produce a model with the least number of predictors, because that just means you've got to collect less data to make these accurate predictions, it seems like that the 2 predictor model is no better than the 1 predictor model. Now, a way that we can formalize this is do just like we did before. We can create a model chi-square 2, let's call it. And guys, remember we did model 1. No, I didn't call it that. I called model 2, didn't I? So model 2, $sign deviance. Minus model, I didn't call this model 1, I just called it model. Yeah, just called it model. Okay, cool. Okay, next thing I'd want to do is I'd want to get my chi-square 2 degrees of freedom. So what I want to do here is I want to go let's see, what do I want to do here? You know what? I think I got that wrong. Yeah, I did do this wrong, guys. I want to take the first model and subtract the second model. So I want to start out with the first model, which I called model, and then I want to come in and subtract the second model. So I want to go from where I started and subtract out. So this is going to give me a So I want to keep that value positive. So because the deviance for the original model should be higher, because as you add a predictor, your deviance should go down. Our question is that did it go down enough to indicate to us that there was a significant improvement in our model? So the next thing I want to do is I want to do my chi-square degrees of freedom for the second time. And what I'll do here is I'll do model $sign degrees of freedom residual minus model 2 $sign degrees of freedom residual. And of course, you could have subtracted that, right? I think 112 minus 111, or 111 minus 110. I'm sorry. Now let's calculate a probability. So we're going to go 1 minus p chi-square, and we need our model, our test statistic, which was model chi2, and we need our chi df2. And we get a p-value that's 0.96. So again, going back to the way that we started this video, our null hypothesis is the model is not better, and the alternative is it is better. So adding this extra predictor, the time spent on my math lab, so to speak, did nothing to increase the effectiveness of our model. So guys, at the end of the day, we can say that our p-value is greater than 0.05. So our second model is not a significant predictor over the initial model. Now, don't get confused with the initial model being the intercept only. The initial model was obviously with the first predictor. Well, you know what? That's all I got for you. I mean, it's not all I got for you. I got a lot more. We're going to get into some really, really cool stuff in some upcoming videos, but that's really all I got time to do today. So, guys, take care.